Hey everyone, welcome to our very last video for kinematics. Now that we have gone through all the content, which is in our previous videos, which you should definitely check out, we will be working through various example problems to help you practice these skills. So example problem number 1. A car is traveling at 30 meters per second uniformly deaccelerates for 50 meters until it comes to a stop before the traffic lights. What is the uniform deacceleration and how much time does it take for the car to stop? So I'll give you 5 seconds to stop this video and give it a shot, and then we shall walk through the solutions. So for these problems, it is purely just using the formulas that we've been using previously. So first up, we're going to use this formula, which is that the final velocity squared equals the initial velocity squared plus 2ax. And we can just rearrange all of the variables to be solving for the acceleration. And when we plug in the values for the initial velocity squared and the final velocity squared, which we know is 0 because it comes to a stop, and the change in x position, which is 50, we get negative 9 meters per second squared. In terms of time, here we're going to be using this formula, which is that the final velocity equals the initial velocity plus acceleration times time. And keep in mind that these problems are labeled out this way because we can use the information from part A to solve for part B. Again, just putting in the variables that we have and the values that we have to solve that t equals 3.33 seconds. What's really helpful for these types of problems is to be labeling out all the various variables that you have, as well as the values that are known and unknown, and therefore we can then solve and eliminate some of the kinematic equations that don't work and are not applicable to the situation. Our second problem, which is very similar to the previous one, a ball is dropped from a tall building. It hits the ground at 4 seconds. How tall is the building? And what was the ball's velocity right before hitting the ground? So again, 5 seconds, pause the video, try out the problem, and then we can discuss it. So how tall is the building? Again, just like before, find the equation that works right for this situation, in which you have all the variables, or at least enough, known. So we can see that we have this equation to be used, that the final x position is the initial x position plus the initial velocity times time plus half of the acceleration times time squared. Because we're solving for the change in x, which would be the height of the building, we don't necessarily need to know what the x positions are, even though you can assume that it hits 0 as the final x position. Here we can use 9.8 as the acceleration, or negative 9.8, depending on your reference frame. We have then just this equation with the 4 seconds from the problem, and we get 78.4 meters. For the second one, we're going to be talking about the velocity right before it hits the ground. So we're going to be using this equation, that the final velocity squared equals the initial velocity squared plus 2ax. So we're going to be solving for, of course, the final velocity. So rearranging the problem, plugging in all of the variables that are known. So we know that the initial velocity will be 0 because it's just dropped off the building. We have the acceleration, which is always a constant negative 9.8 meters per second. We have the change in height here, which we have from back there, and we can solve that the final velocity is 39.2 meters per second. Our next couple problems are going to be based on graphs. So let's start off with this one. A ball is thrown straight down from a tall building. Qualitatively, so that means you don't need real numbers, try to graph these 3 different graphs. So that's position versus time, velocity versus time, and acceleration versus time. Okay, so here's the first one. We have the position versus time, and the ball is thrown straight down from the building. So this is a pretty constant sort of graph, but what's really helpful before we go into position is actually to work backwards. So we know in these type of problems, acceleration, a constant negative 9.8. So we can draw that line straight down there at negative 9.8. Just keep in mind that the graph here is 0 and it's going negatives. It's not the other way around, which might be a bit disorienting. Then we have velocity times time. Know that the slope of this graph has to be a constant negative 9.8. Because it's thrown, which is the key word, we do not have an initial velocity. So we can say that it starts off at the origin at 0 meters per second, and then that the actual slope of this graph will be negative 9.8, so we go straight down. For position, which gets a little bit more complicated, we will have this curve because the velocity is continuously changing. So we do know that we start off at a high position. So we start off at 50, for example, which is just a arbitrary number in this situation, and we just decrease slowly according to this graph as its slope. Another one, a ball is tossed, which is the key word here, straight up into the air. Again, qualitatively graph the following: position versus time, velocity versus time, and acceleration versus time. So again, I'm just going to click through all of these because that makes it a lot easier. So in fact, these two graphs are pretty much the same from before. Again, acceleration, really solid here. Just again, negative 9.8 meters per second squared, and a straight line through. Velocity is really the same graph, but the initial velocity will be different. Here, it's just an arbitrary number at around 15. You don't have to start there. Just make sure that you don't start at 0 here, and you do slice through, again, with a slope of negative 9.8. The really key part in this problem is actually the position versus time graph, because you see here, you start off at 0, and could be another value, but it does have to go to a maximum height. It then slopes off and curves back down just like a upside down parabola. And if you look back here, it will connect to all of these graphs, especially the velocity, because we start off at an extremely high slope right there. And eventually, the slope slows down and reaches 0 at our maximum height, as we mentioned in the previous videos, and then again continues to decrease and become more negative, just like this slope shows. So now we're going to be starting off our last problem, and that is that a juggler tosses a flame torch directly upwards at 3 meters per second. Now we're going to determine the following: the amount of time it takes for the torch to come back to the juggler's hand, the greatest height that the torch reaches, and the height of the torch at speed 2 meters per second. So pause the video and try to give this problem a shot. So first up, time. This equation is in fact not necessarily a kinematic equation, but it is a very helpful formula that we derived in our previous video. So make sure to give that a shot because this equation is super helpful while we're solving various kinematic problems. Just subbing in the variables that are given to us in this problem, and we get 0.61 seconds. Height, again, this formula is again from our previous video where we talk about important formulas that we can use from kinematic formulas. It's just plugging in, again, the variables from before and getting that the height is 0.46 meters. And our last one, which is the height of the torch when the speed is 2 meters per second. This is the formula that we are going to be using because we don't have time, and this is the only formula that doesn't involve time. We don't want to use time because we don't know the time at which the flaming torch is at 2 meters per second. We do know the time at the maximum height. We do know at the initial and final velocity of the time, but not at a specific location. But we do know the final velocity, the initial velocity, the acceleration, and we're going to be solving for x in this situation. So this formula is absolutely perfect. Just plugging in the values again, and we get that x is equal to 0.26 meters. Thank you so much for joining me here today in our last kinematics videos for practice problems. Make sure to like and comment on this video, subscribe to our channel, and check out various other videos from STEMmy on other STEM topics. Thank you so much again for joining me here today.